it wild how some phrases just like catch on? Take machine learning. Sounds super modern, right? But the term itself, Arthur Samuel at IBM coined it way back in 1959.
Yeah, a long time ago. Apparently, it was partly a bit of marketing spin.
Kind of like cognitive computing much later, but machine learning definitely stuck.
It really did.
Anyway, for this deep dive, just to keep it simple, we'll probably use learning and machine learning pretty much interchangeably. Does that sound okay?
Absolutely. Makes sense. And a really core idea here is supervised learning.
Right.
Think of it like this. You're learning, but you have a teacher, a supervisor, showing you examples and telling you the right answer for each one.
Okay, like flashcards.
Sort of.
Yeah.
More formally, we talk about a data set of labeled examples, like a list of pairs. You have an example, and you have its correct label.
Gotcha. Example and label. And the example part, that's the feature vector you hear about.
Exactly. That's the term. A feature vector is basically, well, a vector, a list of numbers.
Numbers that describe the example.
Precisely. Each number is a feature, a specific characteristic. And crucially, the third number in the vector always represents the same type of information for every single example.
Okay, so if we're describing people, maybe feature 1 is height, feature 2 is weight, feature 3 is, I don't know, gender.
Perfect example.
Yeah.
Feature 1 is always height, 2 is always weight, and so on for everyone in your data set.
Makes sense. So how does this play out in something practical, like spam filters? You mentioned that before.
Right. Spam detection is a classic example.
Right.
So with supervised learning, you'd start by gathering a ton of emails, thousands, maybe more.
Okay.
Then you or someone has to go through and label every single one, spam or not spam. That's your labeled data set.
That sounds like a lot of work.
It can be. Getting good labeled data is often a huge part of the challenge.
So you've got thousands of emails labeled, but emails are text. How do they become these number lists, these feature vectors?
Yeah, that's a key step. You need to convert the real-world thing, the email, into numbers the algorithm can chew on. For text, a really common way is the bag of words approach.
Bag of words. Sounds simple.
The basic idea is pretty straightforward. You create a dictionary, essentially a huge list of all the unique words across your emails. Or maybe just, say, the 20,000 most common English words.
Okay, a massive dictionary. Then what?
Then, for each email, your feature vector has one position for every word in that dictionary.
And the number in that position tells you if the word is in the email.
It could. A simple version is just 1 if the word appears, 0 if it doesn't. Or you could make it the count how many times that specific word shows up in that email.
Huh. Okay, that's clever. Turning text into a big vector of counts or presences. What about the labels, though? Spam. Not spam. Still words.
Good point. Yeah, most algorithms need numerical labels too. So you might say, okay, not spam is 0 and spam is 1.
Right. Everything becomes numbers. Features are numbers. Labels are numbers.
Now you're ready for the algorithm.
So what does an algorithm do with all this? You mentioned the support vector machine, SVM.
Yes, SVM is a popular supervised learning algorithm.
Right.
And it actually has its own preference for labels. It likes +1 for the positive class, maybe spam, and might get a 1 for the negative class, not spam.
Okay, so 0 and 1, or +1 and -1, depends on the algorithm. So the SVM gets these vectors and these +1, 1 labels. What's its goal?
Its main goal is to find the best possible dividing line, or boundary, between the positive examples and the negative examples.
In that high-dimensional space defined by the features. Right?
Exactly. If you only had 2 features, you could plot them on a graph. And the SVM would try to find the best line to separate the +1 points from the -1 points.
And in more dimensions, it's a plane or a hyperplane.
Hyperplane, that's the term. It's just the generalization of a line or plane to any number of dimensions. And this boundary is defined by a mathematical equation, usually written as WXB = 0.
Okay, WXB = 0. And
Right.
there's that figure 1 in the source showing this with 2 extra lines parallel to it.
Yes, those parallel lines are key. They represent the margin. See, the SVM doesn't just want any separating hyperplane.
It wants the best one.
Right. And best here means the one that creates the largest possible gap or margin between the hyperplane and the closest data points from either class. Those parallel lines touch the closest points.
So it's like drawing the line right down the middle of the widest possible street, separating the two groups.
That's a great analogy. A wider street, a larger margin, generally leads to better generalization.
Meaning it's better at classifying new emails it hasn't seen before.
Exactly. It's less likely to be thrown off by slight variations.
Yes. Okay, wider margin is good. How does the math make that happen? Something about minimizing W.
Precisely. It turns out that maximizing that margin is equivalent to minimizing something called the Euclidean norm of W, basically, the size of that vector W in the hyperplane equation.
Huh. Minimizing the W vector makes the margin bigger. Seems counterintuitive.
It does a bit.
Yeah.
But geometrically, the distance between those two parallel margin lines, WXB1 and WXB equals 1, everyone, is actually calculated as 2 divided by the norm of W to W. So smaller W means a larger value for 2W, which means a bigger margin.
Oh, okay. The division makes it work like that. Got it. And the source says this basic SVM is a linear model because the boundary is a line or a flat plane.
Correct. It creates a linear separation. But, and this is important, SVMs can also handle nonlinear separations using something called kernels. Kernels are like a mathematical trick that lets the SVM effectively map the data into a higher dimensional space where it can be separated by a hyperplane. When you map it back, the boundary in the original space looks nonlinear, curvy.
Whoa, okay. So kernels let the straight line bend, essentially.
That's a good way to think about it. It makes SVMs really powerful for complex data sets where a simple straight line just won't cut it.
Because real data is messy.
Totally. You often have noisy data, maybe some emails labeled wrongly, or just outliers that sit on the wrong side of where you'd like the boundary to be.
Can SVMs handle that? Or do they need perfectly separated data?
Good question. The basic idea assumes perfect separation is possible. But more advanced versions, often called soft margin SVMs, allow for some misclassifications. They introduce a penalty for points that end up on the wrong side of the margin, trying to balance having a large margin with minimizing these errors.
Okay, so it can be flexible. That seems crucial. Now, the math notation, we touched on it, but the source goes into more detail. Scalars, vectors, sets.
Right, this is just the language we use. Scalars are easy, just single numbers.
Like 5 or negative 3.2.
Exactly. Vectors are ordered lists of numbers, like our feature vector height, weight, gender. You can picture them as arrows from the origin or just points in space. Figure 1 shows this.
And sets.
Sets are just collections of unique things where the order doesn't matter. Like the set of all possible labels, spam, not spam.
Okay. And the notation for elements in a vector, like X superscript J, that little J.
Yes, XJ or WJ. Super important point the source makes. That parenthesis means it's the index, the J at E element. It's not X raised to the power of J.
Right. Got to watch out for that. If you wanted power, you'd write XJ2 or something.
Exactly. Clarity is key.
Then there are those big symbols, sigma and pi.
Summation and product, just shorthand. Sigma means add up all these things, and pi means multiply all these things. Saves a lot of writing when you're dealing with lots of data points or features.
Useful shortcuts. Okay, what about functions, fx and all that?
Yeah, functions are fundamental. A function is basically a rule. It takes an input, we call it the argument, from a specific set, the domain, and gives you exactly one output, the value, in another set, the codomain.
Input, rule, output, like y equals fx, x goes in, f is the rule, y comes out.
Precisely. And x is the variable. We often want to know things about functions, like where they reach their lowest point minimum or highest point maximum. Figure 2 shows this concept.
Finding the bottom of the valley or the top of the hill in the functions graph.
Exactly. And related to that are the max and argmax operators.
Right. What's the difference there?
Max just gives you the highest value the function reaches. Argmax tells you the input, the max value, that produces that highest value.
Ah, okay. One's the peak height, the other's the location of the peak.
Correct. And mine and argmine are the same idea, but for the lowest value. Very useful when we're optimizing models finding the best settings.
We want to find the parameters that minimize the error, for example.
Exactly. We'd use argmine to find those parameters.
And the assignment operator, that omega symbol?
That's just notation for setting a variable's value. Like saying W gets assigned the value 0.5, it means we're updating or defining something.
Simple enough. Okay then. Calculus. Derivatives.
Yep. A derivative tells you how fast a function's output is changing as you change its input just a tiny bit. Think of it as the slope of the function's graph at a specific point.
Steep slope means fast change. Flat slope means slow change.
You got it. And the chain rule. That's just a rule for finding the derivative when you have a function inside another function, like fx, so fx plus 5x plus 1, 2.
Yeah.
It tells you how to handle that composition.
Okay, for nested functions. What about the gradient? That sounds like derivative plus.
It is. The gradient is for functions that have multiple inputs, like our models often do, multiple features.
Like f bake 1 by 2 equals x1 plus b up 2 plus c.
Perfect. The gradient is a vector where each element is the partial derivative, with respect to one input.
Partial derivative.
It's the derivative with respect to one input variable, like by 1, treating all the other input variables, like by 2, as if they were constants for a moment.
Ah, okay. So you find the slope in the direction of each input axis separately.
Pretty much. The gradient vector points in the direction where the function increases fastest. Super important for optimization algorithms that try to climb hills or descend valleys.
Makes sense why that's useful. All right, next up, random variables.
Right. A random variable is just a variable whose value is a numerical outcome determined by chance. It could be discrete, taking specific values like rolling a die, 1, 2, 3, 4, 5, 6, or continuous, taking any value in a range, like a person's exact height.
Okay, and expected value, is that like the average?
It's essentially yes. The expected value EX is the long-run average value of the random variable if you repeated the random process many, many times. And the source mentions the sample, mean just the average of the data you actually collected is usually a good, unbiased way to estimate that true expected value.
Okay, dealing with randomness. Then Bayes' rule, probability stuff.
Yes, Bayes' rule is huge. It's a mathematical formula that tells you how to update your belief about something, a probability, when you get new evidence.
Pay things out.
Updating probabilities based on new info.
And the source connects this to finding the best parameters for a model using a prior.
It does. You can think of having a prior belief about what the best parameters might be before you see the data.
Yeah.
Then, as you process the data, you use Bayes' rule iteratively to update your belief, getting a posterior belief that combines your prior with the evidence from the data.
So you start with a guess and refine it.
Right. Alternatively, there's the principle of maximum likelihood. Here, you don't really start with a prior guess. You just ask, what parameter values make the data I actually observed seem most probable or most likely?
Two different philosophies for finding the best settings. Okay, let's shift slightly. Classification versus regression.
Two main flavors of supervised learning. Classification is when the output is a category label from a fixed set, like spam or not spam. That's binary classification, 2 classes. Or maybe classifying images as cat, dog, or bird.
Assigning labels.
Exactly. Regression is when the output is a continuous numerical value, like predicting house prices or temperature tomorrow.
Predicting a number, not a category. Got it. Then there's model-based versus instance-based learning.
Right. Model-based learning, like SVM or the regressions we'll discuss, uses the training data to build an explicit model with parameters WB, etc. Once the model is built, you don't necessarily need the original data anymore.
It learned the rules.
Kind of, yeah. Instance-based learning, on the other hand, basically memorizes the training examples. To make a prediction for a new point, it looks at the most similar examples, instances, in its memory, and bases the prediction on them. K-nearest neighbors is a common example.
Learning rules versus learning by comparing to known examples. Interesting. And shallow versus deep learning.
Shallow learning typically refers to models where the parameters are learned more or less directly from the input features, perhaps with 1 or 2 layers of transformation. Most traditional algorithms, including the ones we've mainly discussed, fall here.
Okay. And deep learning.
Deep learning uses artificial neural networks with many layers. Deep refers to the number of layers. Each layer learns increasingly complex representations of the data, building on the outputs of the previous layer. It's about learning a hierarchy of features automatically.
Layers on layers, finding patterns. Okay, let's dive into a specific model, linear regression.
Right. Linear regression is often the starting point for regression tasks, predicting those continuous values.
Yeah.
The core idea is simple. Assume the output is a linear function of the input features.
Like a straight line, y equals mx plus c, or fwbx equals wx plus b in the source's notation.
Exactly that, for one input feature. Figure 1 shows this line. If you have multiple features, it's a plane or a hyperplane. The goal is to find the best values for the weight we, or weights, if multiple features, and the bias b.
The best values being the ones that make the line fit the data points most closely.
Precisely. We need a way to measure closely.
How do you do that?
We use a cost function, sometimes called a loss function. For linear regression, the most common one is the average squared error loss. For each data point, you look at the difference between the actual value y and the value predicted by your line, fw/dbx. You square that difference, and then you average these squared differences over all your data points.
So prediction actual 2, averaged, y squared.
Yeah. Squaring does 2 things. It makes all errors positive, so underestimates and overestimates both count as errors, and it penalizes larger errors much more than smaller errors. Also, mathematically, it gives you a nice smooth curve when you plot the cost versus the parameters, which makes finding the minimum easier using calculus, like those gradients we talked about.
Ah, smooth is good for finding the bottom of the valley. Makes sense. And we want to minimize this average squared error.
Exactly. That's the optimization procedure. Find the W and B that result in the lowest possible value for the cost function. That gives you your best fit line.
The source also warns about overfitting here, showing a crazy wiggly line in Figure 2 trying to hit every point. It says linear regression is less prone to this.
Yeah, that's generally true, because linear regression is, well, linear. It's a relatively simple model. It doesn't have the flexibility to wiggle excessively to fit the noise in the training data. That high-degree polynomial in Figure 2 is overfitting. It fits the training data perfectly, but would likely do terribly on new data. Linear regression often generalizes better because of its simplicity.
Simplicity helps avoid memorizing noise. Okay, so
Yeah.
that's linear regression for predicting numbers. What if we want a binary outcome, 0 or 1, like our spam example?
Then we often turn to logistic regression. Despite the name regression, it's actually used for classification problems, specifically binary classification.
Okay, name's a bit confusing. How does it work? Still using WX plus B.
It starts with that linear combination, Wx plus b. But then, instead of using that directly as the output, it feeds it into a special function called the sigmoid function.
The sigmoid.
Yeah, the sigmoid function looks like a smooth S shape. It takes any real number as input, the result of Wx plus b, and squashes it into a value between 0 and 1.
Ah, so the output is always between 0 and 1, like a probability.
Exactly. The output of the logistic regression model, FWBX equals 1 plus e, Wx plus b, is interpreted as a probability that the input x belongs to the positive class, class 1.
Okay, so it gives a probability. How do we find the best W and B for this model, still minimizing squared error?
Actually, no. For logistic regression, the standard approach is different. We use maximum likelihood estimation.
Maximum likelihood. We heard that before.
Right. Instead of minimizing error, we try to maximize the total probability, the likelihood, of observing the actual labels in our training data, given the probabilities predicted by our model.
So if an email is spam, label 1. We want the model to output a probability close to 1 for it. If it's not spam, label 0, we want the probability close to 0.
Precisely. If the model outputs probability p for class 1, the likelihood for a true class 1 example is p, and the likelihood for a true class 2 example is 1p. You calculate the total likelihood by multiplying these probabilities across all training examples, or summing their logarithms, which is easier mathematically, and then find the W and B that make this total likelihood as high as possible.
Maximize the probability of seeing the data we saw. Different goal than minimizing squared error, but gets us the best parameters for this type of problem.
Exactly. It's about choosing the model parameters that best explain the training data we have.
Wow. Okay, that covers quite a bit. Supervised learning, SVM, the math basics, linear and logistic regression. It's definitely a deep dive into the foundations.
It really was. And honestly, we've just scratched the surface. But hopefully it gives a good sense of the core concepts, things like feature vectors, labels, finding boundaries, minimizing costs, maximizing likelihoods. These are recurring themes.
Yeah, you start to see the building blocks. So if you've been listening, you should now have a much better feel for how machines can actually learn from data, at least in this supervised way. It's not magic. It's a lot of clever math and data processing.
It absolutely is.
Right.
A blend of mathematical principles and practical computation.
So thinking about all this, the classification, the regression, turning real things into feature vectors, it does make you wonder what kinds of problems out there, maybe problems you encounter or think about, could actually be tackled using these kinds of approaches. Where could you apply something like an SVM or a regression model? That's maybe something interesting to mull over.